In this video I will try to find very good crystals. So I have bought several different types, 100 of each. They don't cost much. These are 10 megahertz and various different manufacturers. I'm running them in a setup that I have described in a previous video, and you can see here the noise of one crystal. It's labeled now 304, and you can see there are some instabilities. The noise doesn't look quite like random. It has, you can see this here, and there was something here strong. What I'm looking at in the S-meter graph, it's the power within this range plus the power in this range. It's from about 5 Hz to 40 Hz on both sides of the carrier. That's to collect good statistics rapidly. This crystal, it comes as minus 102 and minus 105 respectively. The channels are not quite equal. There is an interesting thing, and that is I will now increase the power. I have here 18 dB of attenuation, so I make it 0. That means I'm sending about 6 dBm through the crystal in a 50 ohm system. And then after maybe 1 minute I go back to 18 dB attenuation. And here you can see clearly a difference. This is what it looked like before, and this is what it looks like now. So running the crystal at a fairly high power makes it shake, and it shakes away dirt, or I don't know. I'm just observing this as an effect that one should take into account. So before continuing, I have already measured some crystals here before I discovered this phenomenon. So I will try to find out how to best clean crystals by power into them, and do that procedure to all the crystals before I measure sideband noise from them. Look at this video, nerds47, for a description of the setup I'm using in this experiment. Here is another crystal. It was originally like this, and here I run it with 0 on the attenuator on my system. These things is when I turned the knobs for balancing the interferometer. As it turns out, unfortunately, some crystals are destroyed when I run them with 0 on my attenuator on the input. That's just 3 dB above nominal power, 0 dBm drive power for the crystal. So I select now crystals that look good at 18 dB on the attenuator, but that also look good after having been subjected to 0 on that attenuator for half a minute. I have bought 100 each of the 4 different types of 10 MHz crystals available from Mouser today. And I have tested, not all of them, because 3 of them are so bad, so it is not worth the time to test all of them. I tested 14 of each, and 10 are useless here, 12 here, and 10 here. 1 good, no good, and 1 good. And this is what it looks like. bad crystals, medium, and good crystals. So one manufacturer makes much better crystals than the other one, the other two ones. So the good ones are these Abacron crystals. And this is just a first preliminary sorting of what is reasonable. And I will demonstrate the difference between these three categories. Here is a good crystal. It has been running for a while, so the balance in the interferometer is no longer perfect. But you can see that from here, that the green and yellow track are significantly below the white, means that the noise is generated in my receivers, the two ones that are uncorrelated. So I tune the interferometer, first the phase, and then the amplitude. And then, of course, I get noise from the tuning thing, which is a variable capacitor. But the noise now is significantly lower. And now it's typical for what I call a good crystal. And I press Alt-Z to clear the correlation. And then I expect the correlated spectra and the normal power spectra to be very similar, because what I'm seeing here is the noise from the crystal, essentially. But this is a good crystal, and good crystals, they may be green or maybe even less than that here, close to the carrier. Here is what I classify as a useless crystal. I don't see the carrier anymore. I have a white region that is at least twice as wide as the carrier. And sometimes the whole screen is white. Here is what I have classified as medium. I can see the carrier clearly, but there are the noise at this close to it go into the red. And what you see here is when I adjusted the balance of the interferometer. Here a crystal is connected in series with a variable capacitor. It's set for about 19 pF, and on the other side the capacitor is grounded, no longer connected to the output connector. So this way I can measure the impedance of the crystal. This is what I see when the spectrum analyzer is set to minus 40 dBm. 10 ohms resistive 10.5 and 5 ohms imaginary part, that's 90 nanohenries. But remember, the crystal is in series with 19 pF. Now I change the power to minus 10 dBm, like that. And you can see the resistive part did not change, not much, but the imaginary part changed a little. It dropped by 2 ohms or something like that. This is a normal crystal among the good ones. Here is another crystal. It looks normal at minus 40 dBm, but when I change the power to minus 10 dBm, like this, it has an abnormal behavior, like this. And this is one of the crystals that I have classified as good from noise performance. There are 2 crystals like this among the 60 ones that are with low noise according to the previous measurement. I have measured now also all the ones that I have classified as useless. they have numbers on the negative side here. They don't differ significantly, not much at least, from the other ones. This is resistance and reactive part at minus 40 dBm, and here at minus 10 dBm. And here are the differences between the power levels. And you can see there are minus signs here, means that the crystal resistive part goes down when the power is increased. It goes, for example, here from 20 ohms to 17 ohms, 3.5 dB, ohm difference. Most crystals that are good have a small change from 0 and or increasing, not much, but a few tenths of an ohm. Oh. Here is one of the odd ones that I'm looking, the particular one I just showed on the network analyzer. And here is one that goes in the wrong direction. This might also be a bad crystal, I don't know for sure. And of course, what did I say? Well, this study did not give much useful information, but I have this data to compare with noise properties when I do more precise measurement of the sideband noise. Anyway, this is the other one which is abnormal. This is a good crystal at a separation of 25 Hertz and 18 dB on the attenuator. And it's characterized by a flat noise floor and a regularly looking waterfall. And here the noise level is minus 146.8 dBc per Hertz. And there is some correlation advantage, about a little bit more than 1 dB. Most crystals are unstable. You can see here is a time when it's better and here it is worse. And it goes up and down like that. And one can see in the S-meter graph that it has bad times and it goes up and down rapidly, and right now it is pretty good. So I take some kind of average of this, and now it is minus 145. And if it is worse than this, I note unstable for the crystal. This one is a limiting case, so I regard it as reasonably stable. This one qualifies to be marked unstable. You can see here. And I take some kind of average of this. Minus 136.5 dBc per Hertz. And there is no correlation advantage, of course, not at these levels. So it goes in here, unstable, and minus 136.5. And of course, this is uncertain by a couple of dB. And I have crystals that are clearly better than this. After having found one crystal that became destroyed by gentle knocking on it, I will test that on all the crystals. Here is one that is unstable, and here is the interferometric result, and I knock gently on it like this. And indeed, now it is very different. And I turn the phase knob, which is this one, and I cannot balance. I have to check the amplitude. And as it turns out, attenuation through this crystal is now higher. So Q is lower. Then I can continue to knock on it. And I see something. And again I check the phase, which doesn't help. And I check the amplitude, and I find it is even more lossy now. And I have reached the end of the amplitude. I have to go here and insert 1 dB more attenuation, going from 1 dB to 2 dB. And then I can adjust. And here I have perfect balance. But the attenuation is about half a dB higher than normal. And this is now very noisy. So I have destroyed this one also. After seemingly have destroyed several crystals, I had to look closer what I'm doing, and I found a poor soldering joint here. So I have redone that, and now I'm testing one of the bad crystals that became really bad when I knocked on the box. But now it looks like this. Here is the interferometer. And it's perfectly stable. This one is actually sensitive to vibration also after I fixed that bad solder joint. But other crystals are not. This one is very unstable. You can see how it jumps up and down. Mainly in amplitude, because the phase adjustment is this. And, well, I have to wait for a while. So there is a change in phase, but there is also a change in amplitude. And then, of course, there is thermal drift, but that's another story. Here it looks like this, and the readout from the S meter tells me that the noise floor is at minus 127 dBc per hertz. I have knocked on the box like before. It didn't change much, but it is less noisy now. So there are some small changes inside. I guess what is involved is the silver epoxy, but I don't know. I have tested all the crystals at 3 different power levels. Minus 16 dBm power dissipated in the crystal and the corresponding attenuator setting. Up to minus 4 dBm, and here are the dBc per hertz levels observed. And then I have sorted in order of increasing power from minus 168 and the worst one among those that I have classified as good was minus 133. So that's more than 30 dB difference. Now I'm going to select the best crystals to use in the next project, a good filter to design an oscillator around. So I'm measuring at the highest level, that is plus 2 dBm, developed inside the crystal. That is a factor of 1.7 above the nominal maximum power, 0 dBm. And as you can see, this one behaves like this. So I didn't see minus 168, but I can see the noise goes from 135 at maximum power, and it goes lower and lower, but it doesn't go lower than minus 158. And the next one like this. And then suddenly I find crystals that behave very oddly, like this one. And in fact, what happens is that the noise is independent of the power. And this is very funny, and I have retested this crystal, and it now behaves like this. So something is very wrong, and I will demonstrate what it looks like. This is the crystal that I found best so far, number 229. And here is the screen, running it at the minus 18 dB setting on the attenuator. I haven't made any change on the calibration, so just look at what the waterfall looks like. And also here is the S-meter graph. And I changed from minus 18 to 12 dB. And of course I have to readjust the phase because the frequency drifts like that, and a little on the amplitude. And here is what I see, exactly the same. And here you can see on the S-meter that the noise seems even to have become a little stronger. And then again I change here, I make it just 6 decibels, like that. And of course again adjust phase and amplitude in the interferometer. And I see now the noise is even a little bit stronger. So, expressed as dBc per hertz, I have increased the carrier from 18 to now 6, that's 12 dB, but the noise has increased only from here, minus 132, to here, minus 130. That's only 2 decibels. So something has happened. The problem turned out to be this 10 pF polystyrene capacitor. It actually looks a little bit ugly. I may have held the soldering iron a little bit too close to it to melt the polystyrene a little bit, but that was long ago and it has worked fine for quite some time, but suddenly it is no longer okay. I have replaced it by 4 series connected 47 pF capacitors, and I'm still running this number 229 crystal. Now things look okay again. This is when I adjusted the interferometer balancing. Here is what the S meter looks like. The adjustment gave some lowering of the noise floor. Before I changed the capacitor, I was seeing minus 130 or minus 132. And now I look here and I see minus 152. That's a 20 decibels change. Now, that which I just showed was with 6 decibels on the attenuator. I have now changed it to 18 decibels, and you see a big difference. And of course, you can see it here as well. I look here, and now I read minus 169. But of course the carrier, minus 160, I'm reading up here. But of course the carrier is now 12 dB weaker. But you can see here that the noise floor I see does not come from the oscillator anymore. It's my test system, or maybe mostly. Here I made a vibration. There is microphonic, and that's from the crystal itself. Here is a crystal with an odd behavior. Sidebands at 100 or 150 Hertz, noise sidebands. I will look at a wider range like this. And here you can see that there is not much noise clear near the carrier, but there is a lot further away. And here's the same crystal at 3 dB higher power. This is 0 on the attenuator. And here is 3 dB less power than the level I had here. So here is 6 dB, 3 dB and 0. So this is a phenomenon that happens at a particular power level. I will not use this crystal. This one is unstable. It jumps between different states. And there is some thermal drift also, of course. I have now looked at the crystals from top in this column, where I sorted the best first and then downwards. But not all the way, because down here all of them seem not so attractive anymore. So down to 149 in this column. And then I placed number 1 here on all that I consider good enough, and I have selected 20 crystals. And here are some that are not quite as good for various reasons. So this is what I will try to make a good filter from. I have the attenuator on 0. That's the maximum power I have used during these experiments. And now I put a magnetic probe to sense the current that is flowing through the crystal and through the capacitors at resonance. And what I see is peak to peak 36 millivolts. And that is 36 milliamps peak to peak. And that turns out to be as expected. 36 milliamps peak to peak, 12.7 RMS, gives me 1.6 milliwatts. That's 2 dBm. I want to use the crystals in a configuration like this. 50 ohms input, a resistor here that is matched by the transformer and perhaps a capacitor somewhere, and a low impedance here, significantly lower than the resistance through the crystal, and then a capacitor to create a high impedance point here where connecting a junction FET, or maybe a couple of them in parallel. So I want to investigate now how much power can I inject here, or rather the other way around. What is the voltage I will get out at this point at the maximum current that I can send through the crystal, which is then about 36 milliamp. That's the highest power I have tested. That's here with these noise values, and it looks quite good, minus 155 up to minus 160. But maybe it's better to run a little bit less power. So I will investigate for power dissipation in each crystal in the order 0 up to maybe minus 5 dBm or so. I'm making a test with this schematic diagram. This capacitor tunes the impedance to be about 50 ohms here. Transformation ratio 7:1 to match to this 1 ohm resistor. And then comes the crystal with about 10 ohms resistance, which means I have a high attenuation. Most of the power goes into the resistor. And then I measure the voltage at the output with the capacitive voltage divider here. And this one is tunable, so I get the resonance at the frequency I want. The network analyzer shows this, a very high attenuation, of course, but the Q is now 115,000 for this crystal. So I haven't loaded it, of course. I mean, it's 1 ohm as compared to the 10 ohms of the crystal. So it is nearly the unloaded Q. And now I connected the current probe in series on one of the legs of the crystal. And it adds some inductance, so the frequency becomes lower. But when I check for the bandwidth, I see the Q is degraded very little. It's now 116,000, so I haven't lost much. As it turns out, I now need plus 13 dBm here to develop most of that power in the 1 ohm resistor, and then to get the current through the crystal at 36 milliamps as the maximum current I was using before. And now I want to find what is the voltage at the output. And what I see across the 1 nanofarad capacitor plus the capacitance of the cable is 123 millivolts peak to peak. And here is the capacitance of the 1 nanofarad capacitor I had underneath here, plus the cable, plus the oscilloscope, 1.22 nanofarads. Again, here's the transmission through this system, minus 27.8. That's what comes through. 27.8 dB attenuation. With this 75 kilo ohm resistor, from here to ground, I get less transmission, of course, there is some loss, and now I have minus 33.6. This means I have lost 6 dB, means half the voltage. So the output impedance of this at the crystal is 75 kilo ohms. The voltage I found, it was 123 millivolts peak, and with the capacitance ratio that turns out to be 38 volts peak to peak in this point. 38 volts peak to peak, 13.4 volts RMS. When loaded with 75 kilo ohms, I have half the voltage, that's 6.7 RMS, which means that the power in the 75 kilo ohm resistor is 0.59 milliwatts. That's minus 2.2 dBm. And this is for an input power of plus 13. So the loss is 15.2. I had expected 13 dB because this resistor is 1 ohm and this is 10 ohms, and when I load for a 6 dB loss, I have 10 ohms more in series. Well, that's the effect of loading at the high impedance point. So 20 to 1, that is 13 dB. So there is an error of 2 dB somewhere, and that's so small, so I don't care about that. I have now computed for all these columns of with good crystals the sum of the power for this one and that one and that one and so forth all the way down, and that at the different power levels. So with the maximum output voltage, the summed dBc per hertz is minus 141, and here I have a sign error, sorry. But now when corrected, I see that the sum is very similar for the 3 highest levels. Means it shouldn't be very critical if I run the crystals at 38 volts output or maybe 19. But going much lower will make the result a little bit less good. So now I will stop this video and start to build something that I will demonstrate in the next video to come.